Here's another example. Domain issue is -1 and 1. That's going to give us vertical asymptotes. So we have vertical asymptotes, x equals -1 and x equals 1. I think what I'll do is I will give myself some room and make each of the tick marks I'm making equal to 1. That tells us we have this vertical asymptote at x equals -1, and this other one when x equals +1. Horizontal asymptote, since we did vertical, let's do horizontal. So we take limit as x goes to infinity of 2x squared over x squared minus 1. And using the technique from 3.4, we multiply top and bottom by 1 over the highest power of x that appears in the problem. And if we work it out, we'll get 2. So the horizontal asymptote is y equals 2. I'll do that one in purple. So y equals 2 is right here. We forgot to do the intercepts, but again, that's relatively straightforward. So y-intercept is when x equals 0, so I do h of 0, and I get 2 times 0 squared over 0 squared minus 1, which turns out to be 0. So that means this function does go through the origin. My x-intercepts are what I get when I let y, or the function, equal 0 and then solve for x. So in order for 0 to equal 2x squared over x squared minus 1, I have to remember an important fact. The only way a fraction can equal 0 is if the top is 0 and the bottom is not 0. So can you think of a number I can plug in for x that will make the numerator 0 and the denominator not 0 at the same time for the same value of x? So hopefully you came up with x equals 0. And if you want to see how to do that algebraically, I can show you right now. This denominator, we're assuming it's not equal to 0, so we can multiply both sides by it, which means we get 0 equals 2x squared, and if we solve that for x, we get x equals 0. In other words, we're getting the same point for our x-intercept, it's just the origin. So we know the origin is in the graph of this function. Now that we have that out of the way, we want to do some calculus to figure out other properties. Okay. So first derivative, what's the first derivative going to tell us? Well, let's take the first derivative first. So at h prime of x, we're going to need to do quotient rule. So it'll be bottom times derivative of top minus top times derivative of bottom all over the bottom squared. So let's see, looks like I'm going to have 4x cubed minus 4x minus 4x cubed all over x squared minus 1 squared. Now I get many questions from you about how much do I have to simplify? Do you want me to simplify more than what I have? Technically, I could just leave it like this if I want to, and I could try to solve for x when I set it equal to 0. But sometimes when you multiply things out and find like terms in the numerator, it actually will sometimes make things a lot easier. Turns out that the 4x cubed cancel out, and we just have nice and simple 4x over x squared minus 1 squared is our first derivative. Now remember, what we do with that is set it equal to 0 and solve for x. Because again, we're looking for the places where the first derivative is positive and where it's negative, and 0 is our dividing line. Using a similar idea as what we did earlier when we were looking for the x-intercept, notice that this fraction, 4x over x squared minus 1 squared, will only be 0 if the numerator is 0 and the denominator is not 0. Again, if I just look at this, I notice that if I plug in 0 for x, I'll get 0 in the numerator. If I plug 0 in the denominator, I'm going to get something non-zero in the denominator, which means my only solution is x equals 0. Let's make the number line then. I just realized I made a really important algebra error when I was simplifying the derivative. I forgot that there's supposed to be a negative in front of the 4x. That's super important, because this expression here is algebraically equivalent to the first derivative. When I'm plugging in test points, I want to make sure that it's an unaltered version of the derivative. So the amount of simplifying you do shouldn't be the type of simplifying where you add or subtract or multiply to both sides of the equation. It should be whatever you do before you do those things, or without any of those things. So I can use this expression to plug in my test points. And I'm going to pick -1 and 1 as my test points. When I plug those in, I notice that the numerator is going to be, when I plug in -1 for x, the numerator is going to be positive. The denominator is always going to be positive no matter what I plug in, unless I plug in -1 or 1 itself. So, since my vertical asymptotes are -1 and 1, x equals -1 and x equals 1, I shouldn't use those as test points. So I'll pick something else. Let's say x equals -2 and x equals 2. Okay? We can still reason in a similar way as I was about to say earlier. So plugging in -2 for x will make this numerator equal to a positive number. The denominator, again, will always be positive as long as we don't pick -1 or 1 for x. So what that means is we have a positive first derivative to the left of 0. When x is 2, I plug in 2 for x. The numerator is negative. The denominator is, again, positive. So I'm going to get that. And what does that tell me? Well, it tells me where the function's increasing and decreasing. Let's go for the second derivative now, h double prime of x. I'm going to use this simpler expression. I'm going to take the derivative of it, and then we'll see what happens. Okay, so bottom times derivative of top minus top times, oops, I forgot the negative again. So bottom times derivative of top. The derivative of the top is actually -4. Minus top, which is -4x, times the derivative of the bottom. To do the derivative of the bottom, we'll actually need to do chain rule. And what's the derivative of the bottom? It's going to be 2 times the quantity x squared minus 1 to the 2 minus first power, but that's just to the first power, so I'm not going to write that. times the derivative of this inside function. The derivative of the inside function is 2x. And that's all over x squared minus 1 squared squared, which gives us x squared minus 1 to the fourth. Maybe simplifying will help things, but I don't know. Let's see. One thing I notice, because I'm trying to look for structure to make my life easier, I don't want to multiply out a million terms and do a million combining of like terms. I want to try to step back and look at structure here. So what I notice is I have at least one factor of x squared minus 1 in each term in the numerator, and I have x squared minus 1 a bunch of times in the denominator. I'm going to factor out this x squared minus 1, and because this first term has two of them multiplied together, there's going to be one left, but that's okay. Let me just write that in my next step. I'm going to factor out the x squared minus 1, and that will leave me with, well, there'll be one x squared minus 1 left over here. There'll be a negative 4. So it'll be negative 4 times the quantity x squared minus 1. All right, and then for the second term, I'm going to factor out this x squared minus 1, so that's gone. I still have, so minus negative 4x times 2 times 2x. That combines to be plus 16x squared. So plus 16x squared. And this is all over x squared minus 1 to the fourth. So again, I have a common factor in the numerator and in the denominator. So I can eliminate those common factors. And I'm going to multiply things out here. I'm going to distribute this negative 4, which means I'm going to now have negative 4x squared plus 4 plus 16x squared all over x squared minus 1 cubed. And then to just make things even simpler, I will have 12x squared plus 4 over x squared minus 1 to the third. Again, to look for concavity, we have to set the second derivative equal to 0, because we want to see where the second derivative is positive, where it's negative. 0 is the dividing line between positive and negative. So I'm setting that equal to 0 and solving. The simplification I just did is helpful because now when I get to this part, when I have to solve something, I'm actually going to be in a better situation. It's going to be a little bit easier to do. So let's see what we notice. Again, we have a fraction that's equal to 0. In order for there to be a solution to this, we need to find an x value that will make the numerator 0 and the denominator non-zero. So first of all, is there any x value that will make the numerator equal to 0? Any real x value? Hopefully you're thinking no, because there isn't one. There's complex numbers that will work, but again, we're only dealing with real numbers here. What that means is there's actually no solution to this. But that doesn't mean that the function has no concavity. What it means is there's no dividing line between positive and negative, between concave up and concave down. There's no different parts of the number line to check. In other words, the number line is just one whole entire thing. The same thing is happening everywhere. Okay, so what does that mean? Well, I have any number that I can plug in that'll work. I can use any number as a test value as long as I don't use anything where the function is not defined or the first derivative is not defined or the second derivative is not defined. So I can plug in anything I want except x equals 1 or x equals -1. So let me pick, I don't know, 5. If I plug in x equals 5 as my test point, first of all, when I plug in 5 here, without figuring out what the actual number is, I know that 5 squared will be positive, and multiply it by 12, that'll still be positive. Add 4 to that, it'll still be positive. If I plug in 5 for x squared, I'm going to have some number bigger than 1 minus 1 that I'm cubing. So I'm going to get a positive number, which means it's concave up everywhere. But that seems really fishy, and I'll tell you why. If I were to choose a number between, let's say, 0 and 1, if I choose 1/2, if I were to plug in 1/2 here, if I used x equals 0.5 as my test point, I'll still have a positive number in the numerator, but the denominator is going to give me a negative number, because 0.5 squared will be 0.25. 0.25 minus 1 will give me some negative number. When I cube that, it's going to still be negative. So the true way that we should have been doing this whole problem is keeping in mind where the vertical asymptotes are. So we really should have put dividers for -1 and 1. And actually, we should probably make that correction here just in case. We might need to make adjustments about what's happening here. So let's give that a try. The test point that we had was -2 and 2 for the first derivative. So we're just going to need a few more just to verify what's happening. So x equals -2 and x equals 2. We did those already. We should probably do one here in the region between -1 and 0, and then one here between 0 and 1, just to be on the safe side. So let's do x equals -1/2 and x equals 1/2. Now, what we were saying earlier, if I plug a negative number into the numerator of the first derivative, so remember that this here is the first derivative, and then just for record keeping sake, that's the second derivative over here. Whenever we plug in a negative number, as long as it's not -1, any negative number we plug into this expression will give us a positive over a positive. Because whenever you square a real number, you're going to get a positive real number. So we know then that both parts here will be a positive first derivative. And then similarly, if we plug in a positive number in the numerator, we're going to get a negative number. And in the denominator, even though plugging in 0.5, squaring it, and subtracting 1 will give us a negative number, we're squaring it here, which makes it positive. So we have negative over positive, which is negative. So it wasn't that big of a deal that we didn't include that in the first derivative analysis. But what about in the second derivative? Well, let's do some test points again. Let's do the same one. So x equal -2, x equal -0.5, x equal 0.5, and x equal 2. So again, I'm trying to determine positive or negative, and I'm trying to do it without calculating anything. I just want to see what kinds of thing I think I'm going to get. So when I plug in -2, actually when I plug in any of these four numbers in the numerator, it's going to be positive. The numerator is always going to be positive for any test point I plug in. The question is whether or not the denominator is going to be positive or negative. Okay, so plug in -2 into the denominator. -2 squared is +4, -1 is 3. Again, I'm not trying to calculate anything. The point here is 2 squared is going to be, or -2 squared is bigger than 1. So when I subtract, I'm going to get a positive number. Cube that, still positive. But between -1 and 0, my test point of -0.5, I'm going to get a negative number inside these parentheses, as I was saying earlier. And when I cube that, it will still be negative. If I plug in 0.5, I'm going to have the same situation. I'm going to have a number smaller than 1 minus 1, which is going to be negative, and I'm going to cube that, which is also negative. And then finally, when I plug in x equals 2, I will get a positive number. So let's take these two number lines and line them up and see what we have. So what we have is increasing and concave up, increasing and concave down, decreasing and concave down, decreasing and concave up. So our graph is going to be let's see, it was increasing and concave up before. So the graph will in some way be like that. And then it was increasing and concave down. So it went like this. And then from 0 to 1, it was decreasing and concave down. And then to the right of 1, it's decreasing and concave up. Now this graph is pretty bad because it's not using the fact that we have horizontal asymptotes. So I need to go back and see what other information I have. So we have a horizontal asymptote at of y equals 2, and we have our one y-intercept. We have just one place where the derivative is equal to 0. So using that fact and using the fact that this function can only be negative between 0 and 1, right? For any other x value, positive or negative, as long as it's outside the interval -1 to 1, I'm going to end up with a positive number. So when I draw stuff that's going below the x-axis, it actually doesn't make sense. And given that there's a horizontal asymptote, it's getting more and more clear that I did something wrong. So let's adjust just these parts of the graph, and then we'll be done. So if I use the fact that I have these horizontal asymptotes and that this function has to be above the x-axis, then I'm in good shape.